Here, the function d sub 0 is what we call as a discrete or a trivial metric. But first, we need to show that the said function d sub 0 is a metric on R. This time, we are going to show the 4 conditions for a said function d to be a metric on a specific set. So we have here m sub 1 or m1 to m4. But before we go to that, let us try to have the proper definition of our d sub 0. The distance of x and y for this said trivial metric or discrete metric is a piecewise function which gives us a result of 0 if x is equal to y, and the value is 1 if it's not, or they are not equal to each other. So those are the two possible results for this given function d sub 0. So we started with that because the first condition for a metric space, or a metric rather, is that the distance for x and y must be greater than or equal to 0. And I'm just going to label this d sub 0 here to just make sure that this is still under the same given function here. Of course, when we use any other value, this is true for all x and y element of our x, okay, or in this case r. Whatever value we use there are two possible answers, 0 and 1, based on our given definition. So no matter would be the value of x and y, as long as they're element of real numbers, we can always get a value for our distance which is greater than or equal to 0. So this means that m1 is automatically satisfied. Okay? It's already satisfied because there are only two possible values, and they are both either 0 and 1, and they satisfied m1. For m2, which tells us that the distance for x sub y, if this is equal to 0, this only tells us that x is equal to y. Okay? But of course, when could we get a distance which is equal to 0? Given already on our definition, 0 is the distance between x and y if they are equal. So the first movement, because it is a bijection, is already satisfied. That if the distance is equal to 0, it tells us that x is just simply equal to y. Now for the opposite movement, of course, when we are going to assume that x is equal to y, and we need to show that the distance is 0 between them, same thing, it was also given on our definition. So if x is equal to y, the distance for x and y is automatically 0. So this is already satisfied by the definition itself. M3 tells us about symmetry, which tells us that the distance between x and y is equal to the distance of, y and x. By the way, I forgot to write here for all x and y, element of x is also here for all x and y, element of x. So we need to show that once we assume this, it will return to this as well here. Now, there are two possible situations that can be drawn here because of our piecewise function. What if x is equal to y? That would mean, per definition, the distance of x and y is equal to 0. Okay? Because they are the same based on the definition itself. Now, looking into that, what is also the result here? The distance of y and x, and since the x and y are equal, should also be equal to 0. This tells us that the distance of x and y is just equal to the distance of y and x if x is equal to y. Now, if x is not equal to y, take note that x and y can take any other values as long as they are element of real numbers. So we need to show that the distance of xy would be equal to the distance of yx. Now, for any value of x and y, as long as they are not equal, the distance is equal to 1. Okay? Because this is what the definition tells us here. It's equal to 1. But this is also true for the distance of y and x, equal to 1 as well, because they are still given to be not equal to each other. In short, the distance of x and y is equal to the distance of y and x satisfies when x is not equal to y. With the two of this in mind, we can now say that M3 is satisfied for both or for all definitions on our piecewise function, because if we have a piecewise function, it should satisfy all for that to be part for a certain function d to be a metric. But still, we're M3. Now let's proceed to M4, and this might probably be an item where we need a lot of discussion here. This M4 tells us that the distance of x and z, this is on triangle inequality, is less than or equal to the distance of x and y, if there exists y, plus the distance of y and z for all x, y, and z element of our x. So same with M3, we're going to assume here whether x is equal to z and x is not equal to z, and let's try to show that this statement is true for both situations. So let's start if x is equal to z. This would mean that the distance of x and z is equal to 0 based on the definition itself. Okay, so how about these two expressions here? Take note that we are considering that x is equal to z. We don't assume, or we did not give any value for y, whether it's equal to x or y or z or not equal. But if it is equal, the distance of x and y, if x is equal to y, then this is equal to 0. And since x and z are equal, that would mean the distance of x, this is y and z is also equal to 0. All of this, we can plot here. 0 is less than or equal to 0 plus 0 satisfies that. So that's the first part. I'm just saying the first part when x is equal to z. Because if x is not equal to y, that would mean z is also not equal to y, because x and y are the same. We would assume here that this is still 0. What will happen to this expression here if x is not equal to y? That's 1. And plus, this is also equal to 1. Obviously, 0 is less than or equal to 2, and it satisfies the same here. With both of these conditions, we have satisfied the first situation if x is equal to z. Take note, under this are two other cases with x is equal to y, and if x is not equal to y, which is also true for z is not equal to y. Now, what if x is not equal to z? That would mean the distance of x to z is equal to, so 1. So this part here is 1. Let's see if this will still be greater than or equal to, the sum is greater than or equal to 1 here. If x is not equal to z, and let's say if x is equal to y, that would mean z is not equal to y, okay? Because x is not equal to y, right? Okay. That would mean the distance of x and y is 0, and the distance of z, it's based on the definition here, this should be y and z. Distance of y and z, since they are not equal, is equal to 1. Plotting them all together, the distance of x and z, which is 1, is it less than or equal to the distance of x and y plus the distance of y and z? Let's find out. 0, 1 plus 1. So 1. So since we have equality, so it satisfies the first part of this situation. Now, I don't have much space. Hopefully, I could generalize it later. If x now still is not equal to z, but we can say here that x is not equal to y. Okay? So if x is not equal to y and x is not equal to z, we can still say that z is equal to y, right? Okay? So we have here x, z, it's 1. Okay, let's find out. X, y, they are not equal, 1. Plus distance of y and z. So if these two are not equal, because we cannot draw a conclusion from here. If these two are not equal, so that's 1. Obviously, it's greater than that. If they are equal, still, this would be 0. So it still satisfies the condition. So all of this under M4 tells us that it is actually satisfied. Take note that we are considering all possibilities here because we have piecewise function which tells us two situations. So all of this with M1 to M4 already satisfied, we can say that the discrete the D sub 0 is a metric on R. Specifically, it's called as a discrete metric or trivial metric. And of course, we can further say that R D sub 0 is a metric space, specifically a trivial metric space or a discrete metric space. That's it for this video when we talk about showing whether the discrete or trivial metric D sub 0 is a metric on R. Thank you very much for watching.